Okay guys, Assalamualaikum and good day. So this will be our first video lecture. First video lecture chapter berapa ni? Non-linear systems. But first let me introduce myself. So I will take the second half from Dr. Hasriza. I will cover two chapters, namely nonlinear systems, the first one, and the second one is digital systems. Digital systems. So just two chapters for my parts. And for assessment, there will be two quizzes. Okay. So assessment. Okay, there will be two quizzes. Two quizzes. Okay. And then two assignment. And one mini project. Okay, so that for my part. But the scope for the mini project cover what you have learned throughout this course. Okay, not just my part. And for my style, I will give a video lecture during the lecture day. And students have to answer some question related to the video within 24 hours from the time that video is given. Let's say now is 5 p.m. I give you one video lecture, and within 24 hours you have to answer a few questions before 5 p.m. tomorrow. Okay, so one Google form will be provided, and there are questions, and there is a section where students can ask questions regarding the video lecture that have been given, and I will take that as a attendance and quizzes. Okay, now, so for today's lecture, nonlinear system. So for today's lecture, nonlinear systems. Okay. So what is nonlinear systems? Let's compare between nonlinear and linear systems. Okay. So we have two part. Oh, tak boleh macam ni. Okay. Okay. So it's a nonlinear. And this is the linear system. Okay. So what you have covered before, everything is in linear systems. Okay. Before only linear system. Let's say you have a spring mass damper system. Okay, you have learned before. Spring mass damper systems. Okay, so then you convert to state space. You get x dot equal to ax plus bu. And y equal to cx plus du. Okay, so you can see that by using modeling process, you can get the equation that represent these models or the systems. And from the equations, you can know either the system is linear or non-linear. So for example, let's say we have one equation. Okay, you buat modeling process, and then you get the equation that represent these systems. X1 dot equal to x2. X2 dot equal to negative 2 x1 minus 3 x2 plus u. So this is the equation. Let's say this is the equation that represent the systems. So based on this equation, how can we identify either the system is linear or non-linear? So it's based on the linear and non-linear system characteristics. Okay, we discuss after this. Okay, first, I just want you to know that from the equation, you can identify either the system is linear or non-linear. Okay, that's number one. Okay, for linear system, how we can use graph to represent the linear or non-linear systems? What the difference? Okay, for linear equations, tengok kat sini. For linear equations, okay, if you plot the graph from the linear equations, you get the graph something like this, the straight line. Or from the graph, you can simply get the equations that represent the graph. So this is the linear systems graph. Okay. And for non-linear systems, okay, well, for the non-linear equation, or non-linear system output, if you plot the graph, it's something like this, the curve. Okay, suka hati dia lah. Yang mana? Okay. So it's curve graph, and you cannot predict the equation that represent the graph. So this is the difference between non-linear and linear graph. Okay. For linear graph, linear equation, you can simply identify the equation by looking at the graph. While for the non-linear equation, it's a curve graph. Okay, it's not easy to identify the equation that represent the graph. Let's say you have a system. So you do some modeling and you get a state space equations. X1 dot equal to x2, x2 dot equal to negative 4x1 minus 1 minus x1 squared times x2, and then you expand it, you will get x2 dot equal to negative 4 x1 minus x2 plus x2 times x1 squared. Okay, so let's say this the equation that you get after you did the modeling process, and this the state space equation represent the systems. Okay, this equation 1, and then equation 2. Okay, so we write back x1 dot equal to x2 equal to negative 2x1 minus 3x2 plus u. So what's the difference between equation 1 and equation 2? Okay, if you can see here, for equation 2, for x1 the power is 1, x2 the power is 1, and x2 for the first equation the power is 1. While for equation 1, x1 dot equal to x2's power is 1. Equations 2, x2 dot equal to negative 4x1 minus x2 plus x2 x1 squared. So this power is 1, power is 1, power is 1, and here is power is 2. So when the question have the higher order more than 1, okay, like this, So this is the first criteria for nonlinear system. Okay. Okay, another one. X2 times X1. Okay. Color biru pula. Okay. X2 times X1 squared. So this is the second criteria for nonlinear system. So X2 times X1 squared. Okay, second criteria. Second criteria for nonlinear system. And the first one, the higher order x1 squared. Okay, the higher order is more than 1. Okay, ni the first criteria for nonlinear system. Okay. So second criteria for nonlinear systems. So it show that x2 and x1 squared is dependent to each other. Dependent to each other, each state. While if you can see for equation 2 kat sini, here is negative 2x1 and negative 3x2, both state x1, pen kena merah, x1 and x2 is independent or is stand alone. Okay, so every time you see these two criteria, first, the higher order in one equation, the higher order is more than 1, so it's a nonlinear system. And the second one, if there are any dependent state, something like this, so that's represent the nonlinear system. Okay. Okay, now let's summarize the difference between linear and nonlinear again. Okay, so for nonlinear systems and linear system, let's say you have one examples, x1 dot equal to x2, x2 dot equal to negative 2x1 minus 3x2 plus u. So what we can say here, pen merah, so x, or we can call it a state. Okay, the higher order for the state, either x1 or x2, is 1. The higher order equal to 1. Okay, so x1 on the power of 1, x2 power of 1, x2 power of 1. Okay, number 1. And number 2, each state is independent. Salah eja pula. Independent. Okay, so that's the different, the first, the two criteria of linear system. While for non-linear system, say I give you one example. Okay, x1 dot equal to x2, x2 dot equal to negative 2 x1 minus 3 x2 minus x1 power of 3 x2. Okay, so here warna biru. Okay, so higher order is equal to 3, so it's more than 1. is more than 1, the higher order. And the state between x1, x2 is dependent to each other. Okay, so this how we summarize the difference between linear and nonlinear systems. Okay. Okay, next is phase plane graph. Okay. Phase plane graph. Okay. So phase plane graph is a state graph. Okay. So we plot x1, x2, x3, or x1 dot, x2 dot, x3 dot. Okay. So in the lab, you refer to Y graph or output response graph. Okay, so we cannot determine either the system is linear or non-linear by look at the output response of the systems. Okay, but we can use phase plane graph to determine either the systems is linear or non-linear. But first you have to know what is the phase plane graph. How we plot the phase plane graph. So graph, we have two axes. Okay, so y axis we use x1 or x2 or x3, while for y axis we use x1 dot or x2 dot or x3 dots. Okay, so that is phase plane graph. Okay, so you have to know first what is phase plane graph. Okay, so now what is the important key point or important topics in this chapter? Okay, so what is the key point on this chapter? So there are 3 key points you have to understand or you have to know. The first one is equilibrium point. Equilibrium point. So this is the first one, equilibrium point. Second one is linearization. Linearizations. And the last one or the third one is Lyapunov. Lyapunov. Okay. So linearizations mean that you convert nonlinear equation to linear equations by using approximations. So that's the definition of linearizations. While Lyapunov, we want to check the stability of the system. Okay, so for today we will cover topic number 1, and number 3. Okay. Okay, so as I mentioned earlier, phase plane graph. So this for nonlinear systems. Nonlinear system, as you can see the curve, it's not a straight line. So now, what is the equilibrium point? Equilibrium point. Okay. So let's say the first examples. Start from here and end at the origin. Okay. And then wind block. Same goes to here. It start from here and then end up at the origin. Okay. So equilibrium point is the state where the point where the state is not moving or stay or rest or stables. So obviously, in the first example, the state is moved to the origins. Here, right? From here to the origin. From here to the origins. So the last point is x1 equal to 0 and x2 equal to 0. Let's say if you have one equations, okay, for examples, x1 dot equal to x2, x2 dot equal to negative 3x1 minus 2x2 squared. So if x1 equal to 0, so you substitute the value in the equations, so you will get x2 dot is equal to 0. So obviously the state is not moving, so we call this as the equilibrium point. Okay, so if the state is not moving, 0, 0, so this systems is stable. If the state is not moving, the systems is stable. As you can see, the location of the poles is at the left hand side of the S-plane. So the system is stable. Okay, now second examples or second phase plane. Okay. So from 0, 0, here is 0, 0 or the origin. Blue color. The state direction go to something you do not know. First one, okay, the directions. And the second one, start from origins to the directions that you do not know. So you cannot predict the value of x1 and x2. And obviously, since you cannot predict the value of x1 and x2, so x2 dot is not equal to 0. And the state is always moving. State is always moving. So for this type of system, we call as unstable systems. Okay, the state is always moving, and the location of pole is at the right hand side of the S-plane. Okay, so this system is unstable systems. Okay, now the third examples, same goes to this one. The state is moving. Okay, color lain lah, biru. State is moving. The state is moving. The state is moving. But you can predict, since the coordinate is repeating, if move in the circles. Okay, so the coordinate is repeating. The coordinate is repeating, and you can predict the value of x1 and x2. The value of state is repeating. The state is moving, but you can predict the value of x1 and x2. So in these conditions, we call as marginally stables. Stables. Okay. And the locations of the pole is on the y-axis. Okay. So stable systems, the state is not moving. Unstable systems, the state is always moving. Marginally stable systems, the state is moving but is repeating coordinates, and you can predict the value of x1 and x2. Okay, now phase plane. Okay, so something like this. Okay, so here is the curve. So here is x1, y-axis is x1 dot, always equal to x2. Okay, so we draw the graph something like this. Let's say you go ride a bicycle. So here is the positions of you and the bicycle. And the bicycle. Okay. So based on the position of the bicycles, so the bicycle can go either to the right or to the left, right? So let's say here is the pond full of the crocodiles. Yeah, this crocodile. Kaki dia. Something like this lah. Okay, crocodile. Okay. Well, here is the safe place. Let's say it's a coconut drink stall. Something here where you can get a coconut drinks. So, if you here and your bicycles, which direction do you prefer to go? Of course, the coconut drinks straw. Coconut drink stall, right? Compared to the pond with a lot of crocodiles. So what is here? Here is the risky position. Risky positions. Like 50-50, is it? Either is die or joy. So here, what we call as a unstables equilibriums point. So you either go to the direction that you can predict, which is here, or you either go to the direction you cannot predict, or the here is dangerous. You cannot predict. It's crocodile there. So if you are the designer, which point do you want to choose? Of course not, because if you're a designer, do you want to choose these positions? Of course not, because it's quite risky. And let's say you have another position. Okay, you and your bicycle is here. Okay, so the bicycle only can slide to the right because it has no energy to climb up. Okay, cannot pedal up, so it's either go to the right. It's only go to the right. And so the bicycle will only move in this part, right, until it stops. So why we talk about this? Because we want to show, or we want to find the coordinate to get the stable equilibrium point. So it shows that if you choose the wrong equilibrium point coordinates, the system will be unstable. So if here is the coordinate, choose the right coordinates in order to get a stable equilibrium point. So point number 1, equilibrium points. So here what you want to do is that we have to choose the right coordinate in order to make sure, or to get a stable non-linear system. Okay, that's point number 1. Okay, next is Lyapunov systems. We already covered the equilibrium points. Next is Lyapunov systems. Okay. Okay, Lyapunov. So, what is Lyapunov? Lyapunov theorems. Okay. So normally in linear systems, how you determine the system? Either the systems is stables or unstables. Macam mana? By the positions of the poles, kan? The poles. Let's say you have one system, one transfer function, gs equal to somethings, s squared plus 3s plus 2. So this is the characteristic equations. Okay. So you factorize the characteristic equations, then you get s plus 1, s plus 2 equal to 0. So s equal to negative 1, s equal to negative 2. So now you can know the position of the pole, either its system is unstable or not. Okay. What if the systems give you one transfer function, something like this? gs equal to s squared s power of 3 plus x1 x2 squared s squared plus x1 power of 3 s. So this characteristic equation is not easy to factorize, but we want to determine either the system is stable or not. So here is the Lyapunov theorems. Okay, so we use Lyapunov theorems to determine the stability of the non-linear system. Lyapunov functions. Okay, Lyapunov functions, we go one by one. Lyapunov functions is used for stability analysis for a nonlinear system if, number one, V naught greater than 0, so the system is unstable or the energy increasing. V naught equal to 0, so the system is naturally stable or the energy stay the same. And the third one, V naught less than 0 and the system is asymptotically stable or the energy decreasing. So as you can see, the Lyapunov is based on the energy equation. Energy equations. So we have a timeline. Let's say, warna biru. We have 3 timeline. Okay. Here is energy positive. So here is where the position of V naught greater than 0. Here is energy negative, and where the position for V naught less than 0. And then here is the energy didn't change or stay. Didn't change. Where V naught equal to 0. Okay, so we have 3 timeline. Okay, energy negative, V naught less than 0. Energy positive, V naught greater than 0. Energy stay or didn't change, V naught equal to 0. So now, what is the equation for energy or kinetic energy? E equal to 1 over 2 mv squared. So if we differentiate this, we get E dot equal to mv v squared. Something we're familiar with. So here is the future value. We want to predict the future value for energy. Okay. So what does this mean? Based on the timeline, if the energy is positive, the system is unstable. If the energy is negative, the system is stable systems. While if the energy didn't change, the system is marginally stable or naturally stable. Okay, so what does this mean? What is this? Okay, now back to you, bicycles, crocodile and coconut drink stall. Okay, so this is the graph. Something like this. I draw it again. Okay, so we have curve. Ding, 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 ding. Here is the crocodile and so on lah. Right? Okay, let's say you have ball. The location of ball is here. Okay. So, kinetic energy. Balls can roll only to the right until it stops moving, right? From right, and then it slowly stop at these positions. So at here is these positions. The kinetics energy E is decrease or negative. So the systems is stable. Let's say another positions is somewhere here. So the balls can roll to the right and it will keep moving. Okay, the ball keep moving. So it means that the kinetics energy E is increase or positive. So at these positions, the system is unstable. Okay, so it's all about the kinetic energy. The ball is keep rolling, so the kinetic energy is increased or positive. So the systems at these positions is unstable. While in these tables, in this position, the kinetic energy is decreasing until it stops. So the system is unstable. How about the marginally stable systems? Okay, marginally stable systems. Okay, we go to the phase plane. So the system is keep repeating or in same coordinates. Kenapa? Ni lah. Okay, same coordinates. Same energy. Or the energy is didn't change. The energy is didn't change. So the system is marginally stable. So this all what we call equilibrium points and Lyapunov. We have go through apa kita tengok tadi? Lyapunov and the equilibrium points. Okay. So I think this all for my first video lecture, and then I will give you a few questions regarding this video lecture, and please submit before 5 p.m. tomorrow. Okay guys, have a good day. Thank you.